Hello everyone. So today, if you remember last class, we just tried to understand the underlying philosophy of displacement method, and then finally we saw there are two important ingredients. One is fixed end moments and another one is stiffness coefficients. What we do today is we will see how to determine those fixed end moments and stiffness coefficients. Okay. So today is lecture 48 and the topic is fixed end moments and stiffness coefficients. Okay. Now, this was our last slide in the in previous class, and these are the fixed end moments, these are the fixed end moments, these are the fixed end moments, and these are the stiffness coefficient. Okay. What we do today is we will see how to determine these moments and the stiffness corresponding stiffness coefficients. Okay. Now, stiffness moments are fixed end moments are essentially, if you see this, if this is our actual structure which is subjected to external load, then we can get the primary structure like this. So, all these corresponding all these joints which we take as unknown, which the corresponding displacements are taken as unknown, those joints are now replaced by fixed joints, and then we can divide this entire structure into small statically kinematically indeterminate structure, and all the beams are now all the segments are fixed beam. Okay. Now, this is a fixed beam which is subjected to external load, and because of this external whatever moments generated at these ends, they are called fixed end moments. Okay. Now, let us see how to find out these fixed end moments. It is there is nothing new in it. You already know it how to do it. Just for the completeness, we are discussing this today. Okay. We will take two examples. First, consider a fixed beam which is subjected to a concentrated load at the midspan. Say that load is set up P, concentrated load at P. Okay. And corresponding moment will be, and corresponding moment this will be, this is A, this is A, this is B, and say this is MB and this is MA. Okay. Or you can use M superscript F to say it is fixed end moment. Okay. Now, this is a statically indeterminate problem. You see here our objective is just to get the support reactions. Reactions means not all the reactions, only the moments at A and B. Okay. And now, there are 3 support reactions here, there are 3 support reactions here. So, total 6 unknown, it is a statically number of equations available is 3. So, it is a statically indeterminate problem, statically indeterminate structure. So, we need to find out what is now what we can do is so let us first we can apply for instance, we have already seen how to determine statically indeterminate structure using force method, right. So, we can apply force method to find out the MA and MF. Okay. Now, again we have run different force methods, mainly method of consistent deformation, but written in a different form. We can apply 3 moment theorem that we discussed in the last week to get this moment. Okay. And what is 3 moment theorem? 3 moment theorem said that your if we take a beam like this, suppose if we take a 3 span, if we take a beam like this, this is A, this is and this is A, B, C. Then the moments at A, B, C, the relations are M A into L A B by E I of A B plus 2 M B L A B by E I of A B plus L B C by E I of B C and then plus M C by E I of B C, that is equal to minus 6 A A B into X A B divided by E I of A B. When I write E I of, it is entire E I of A B, L A B minus 6 A B C X C B by E I of B C B C into L B C. This was 3 moment equation, if you remember. Now, another thing also we discussed, suppose in this case, since it is a fixed support, now what we can do is we can assume this is A B maybe, this is B maybe, this is B maybe, and then we can assume a fictitious beam, a fictitious, say this is C, this is C here, and which is again fictitious beam for which E I is equal to infinity, E I is equal to infinity, isn't it, because it is fixed support. Now, similarly we can assume another, it is another, say it is D, and then here also E I is equal to infinity. Okay. So, it has become 3 span beams, span C A, A B and B D. Now, we apply, then we have moment here M C, moment here M A, moment here M B and moment here M D. Okay. Now, we can apply 3 moment equation, this equation at A, and we can apply 3 moment equation at B, get 2 equations for M A and M B, and then solve these 2 equations to get the M A and M B. Since for this span and for this span E I is infinity and we have 1 by E I term in this equation, the corresponding term for this and for this segment will be 0. And finally, the equation that we get is this. And what is A B and A B? A B is the bending moment. If you take a primary structure by inserting 2 hinges here at A and B, then this becomes a simply supported beam subjected to a concentrated load, and the bending moment diagram of that beam, area of the bending moment diagram of that beam is A B, and the distance of the centroid of that bending moment diagram from A will be X A B. Now, for this, what will be the bending moment diagram? If we insert 2 hinges here, then the bending moment diagram will be, it becomes a simply supported beam subjected to concentrated load at the mid span. So, this will be P L by 4, right, and this is A, this is B, this is A, this is B, and this is the centroid which is at a distance L by 2, L by 2. From here also it is L by 2, and for this segment BD, for BD and for AC, we do not need anything, because anyway this corresponding, these values will be 0. Okay. So, now we apply these 3 moment equation at A and again these 3 moment equation at B. If we do that, then the corresponding equations that we get is M A is equal to M A plus 2 M B is equal to minus 6 into A B of this diagram. A B of this diagram is half into P L by 4 into L, then into distance from A, it is L by 2 divided by L square. Okay. So, this is one equation we get. Now, this becomes minus 3 P L by 8. So, M A plus 2 M B become this. Okay. This is equation number 1. Okay. Now, Similarly, similar to this, we can have one more equation, and that is m a plus, that is m a 2 m a 2 m a plus m b is equal to minus 3 p l by 8. Okay. Now, if we solve these two equation 1 and equation 2, then we get m a is equal to m a is equal to m b is equal to minus p l by 8. So, this is the fixed end moment. This is the fixed end moment. Okay. So, this you can write, this is m a f, m a f. So, this is the fixed end moment. So, if any structure which is subjected to a load like this, fixed beam subjected to a concentrated load, corresponding fixed end moment will be this. Okay. Now, let us do the similar exercise for another case. Now, this time we take another structure like same structure, but fixed structure, it is fixed end moment, your beam is always fixed beam. Now, it is subjected to uniformly distributed load. Okay. So, this is A, this is B, and this is Q, and again we can apply the 3 moment equation, and if we do the 3 moment equation, then for this case we will get, we assume that there is a beam here which is C, and there is another beam here which is D, and for this it is E I is equal to infinity, for this also it is E I is equal to infinity, and then apply 3 moment equation at A, 3 moment equation at B, get the 2 equations and solve them. If we do that, then we get for this problem m A is equal to m B is equal to minus q L square by 12. Okay. Now, similarly for any loading condition, when you determine the fixed end moments, essentially then you are solving a statically indeterminate structures. We know how to solve statically indeterminate structure using force method. So, you can apply those force method to get the corresponding fixed end moments. Now, if you see this, there are that is already available in the book, but do not take it these values for granted. At least once you should compute the fixed end moments for different loading conditions, and then see whatever moments you are getting that are you are getting these values. Okay. If you take any structural analysis book, these fixed end moments for different kinds of loading are already given there. Okay. So, fixed end moments we know, right. Once we know the fixed end moments, we need to, if you remember, the equations were f is equal to k into d, right, and f is, in order to get f we need fixed end moments. Now, we have seen how to determine fixed end moments. So, this is now known, this is now known. Now, we need to find out now what is stiffness matrix. Now, stiffness matrix means what is stiffness coefficients. Once we know the stiffness coefficient, then we can apply this equation. Now, again for stiffness coefficients, we take 3 cases, but different boundary conditions for different loading, you can similar approach you can apply to get the stiffness coefficients. For instance, okay, take a propped cantilever beam. Okay. Now, which is subjected to a moment B here, and because of that it undergoes rotation like this. Okay. So, this angle is theta B. Okay. Now, what and then corresponding moment at this end is generated as m A. Okay. Now, what we need to find out here is, first we will see, forget about stiffness coefficients and flexibility coefficients. Let us treat this as a statically indeterminate problem, a propped cantilever beam which is subjected to a moment at the propped end, and then what we need to find out? We need to find out what is the corresponding rotation at the propped end. Okay. Now, the problem is this. Okay. Now, so this is a fixed, this end is fixed end and this is a propped end. Okay. Now, one moment is applied here, and this moment is say m. say it is MB, MB because it is applied at B. Okay, this is end A, this is end B. Okay. Now, corresponding rotation is this. Since it is fixed end, there is the slope is 0, and at B it is hinge end, so there will be non-zero slope, and this slope is, suppose this slope is, this angle is theta B. Okay. So, it is slope at theta B. Now, suppose this distance is delta A, okay. So, or you can write delta AB as well. So, delta A is essentially the deviation of A on slope drawn at B, isn't it? So, at B you draw a slope, and on this slope what is the deviation of A, say that is equal to delta A, or you can write delta AB as well. Okay. Now, next is, suppose if we do not know what is these values, corresponding moments here is, say it is MB. Okay. What we need to find out, we need to MA, sorry, it is MA. We need to find out how this theta B is related to MB and MA. Okay. Now, let us first find out, let us first draw the bending moment diagram. If we know it is the moment at B is MB and moment at A is MA, there is no other forces in between. So, bending moment at B will be MB, bending moment at MA is MA, and in between they vary linearly. Okay. So, the bending moment diagram will be, so this is MB and this is MA. We do not know whether MA is more what value. So, this is MB. Okay. So, this is the bending moment diagram, right. This bending moment diagram is positive, this is positive because when we draw the bending moment diagram, then the sign convention we use, whether it is sagging moment or hogging moment, we have taken it is sagging moment. So, the bending moment diagram is positive. Okay. Now, remember moment area method. What moment area method says is that the angle at B will be angle B theta B will be the area of this diagram. Suppose this is not, this is MB by EI, moment M by EI diagram. So, moment area method says that the slope will be area of this diagram, right. So, theta B will be area of this means it will be half of MA plus MB divided by EI into L. Okay. So, this is theta B. Suppose this is equation number 1. Okay. Now, we also know that the second theorem moment area method, that the deviation of A on slope drawn at B is equal to moment of MI by M by EI diagram from A. So, moment of this diagram from A will give us this deviation. So, delta A will be, then delta A will be the moment of this about this, and moment of this about this will be the area multiplied by the distance. So, area will be MA plus MB divided by 2 EI into L, that is the area of this, and that multiplied by the centroidal distance. This is a trapezium, centroidal distance of a trapezium is L by 3, and then it is MA plus 2 MB by MA plus MB. Okay. This is delta A. So, delta A then becomes this MA and this MA, they get cancelled, and this become L square by 6 EI into MA plus 2 MB. MA plus 2 MB. Now, what is delta A? Now, delta A, that was our assumption right from the beginning, that the displacement and slopes are small, then linear superposition is valid. So, if delta A is small, then we can write delta A is equal to theta B multiplied by L. So, this delta A is essentially theta B multiplied by L. So, what we get from this, theta B is equal to MA plus 2 MB by 6 EI into L. Okay. Suppose this is equation number 2. This is equation number 2. Now, let us solve equation number 1 and equation number 2, find out MA and MB in terms of theta B. Okay. Now, if we do that, then what we get is MB is equal to 4 EI by L into theta B, and MA is equal to minus 2 EI by L into theta B. Okay. Now, let us write this in a different form. This, let us write it as MB is equal to MB is equal to KBB into theta B, and MA is equal to KAB into theta B. Okay. What is KBB? KBB is this and KAB is this. Okay. So, KBB is the KBB and KAB are the stiffness coefficients. Okay. Now, why it is KBB essentially what? KBB is the relation between moment at B and rotation at B. Okay. So, this is KBB, and similarly KAB is equal to the relation between the moment relation between moment at A and theta at B, or in a different way we can say that KAB is the if we applied unit rotation at A, then corresponding moment generated unit rotation at B, then corresponding moment generated at A will be KAB. Okay. This is the stiffness coefficients. So, when we construct this these stiffness coefficients, if K11, K12 and so on. Now, if we see the boundary conditions of the beam is such that it can be idealized as the problem that which now we have seen, then we know what would be the corresponding stiffness coefficients. Okay. Now, let us take one more example where it is slightly different. Here, now, the example is the second example. Now, same thing, but now instead of fixed support at A, so make it a hinge support. Okay. Now, there is a moment at MB, it undergoes deformation like this. What we need to find out, how this MB is related to theta B and theta A. Okay. Now, let us do that once again. So, take this is okay. Now, we can this is subjected to we have a moment which is MB here, because this is A and this is B. Okay. Now, you could have taken hinge support here, both will give you the same thing, because there is no horizontal load. So, horizontal reactions will be 0. Okay. Now, this will undergo deformation like this, and this angle is theta b. This is theta b, and this angle is, similarly you can have an angle like this, and this angle is theta a. Okay. We need to find out what is the relation between MB, theta b and theta a. It is very straightforward. This is a statically determinate problem. So, we can apply the conjugate beam method. The conjugate beam method says that you first draw the bending moment diagram of this beam. The bending moment diagram will be this is MB positive here, and then there is no bending moment at E. So, it is linearly varying. Okay. Now, next the conjugate beam says that whatever bending moment diagram you take, you assume that as loading diagram on the conjugate beam. And conjugate beam, how to form the conjugate beam? Conjugate beam, it is the same length, same beam, but the depending on the support, the boundary condition, the boundary condition in the conjugate beam will be different. But for simply supported beam, the conjugate beam is also simply supported. So, it is a conjugate beam, right? It is a conjugate beam which is subjected to a load like this. And then conjugate beam says that if you get the reaction at any point, that reactions will give you the corresponding rotation. Okay. So, let us find out what is the reaction. So, at this point your reactions is AY, and this point your reactions is BY. This is A, this is B, and what is BY? If we take a moment about A, then BY will be ML by MB into L by 3 EI. Okay. And if you take and AY will be ML by MB into L by 6 EI. Okay. So, this is BY and AY. Now, since BY is equal to theta b and AY is equal to theta a, so theta b will be MB into L by 3 EI. So, which can be written as MB is equal to 3 EI by L into theta b. And similarly, MA can be written similarly theta, similarly in terms of theta b, in terms of theta a, MB also can be written. Now, this is the flexibility coefficients. So, what we can write is, we can write MB is equal to KBB into theta b, where KBB is the moment at B due to the unit rotation at B. Similarly, MB can be obtained as KB into KBA into theta A. Theta A will be this will be theta B, and this will be theta A. Right, that is conjugate beam method. So, similarly, MB can be obtained as theta. So, KBB will be these corresponding stiffness coefficients. So, it essentially says that it is the moment generated at B, due to the unit rotation at A. So, KBB was the moment at B due to the unit rotation at B, and KB is the moment at B due to the unit rotation at A. So, this is the flexibility coefficient. Again, the problem when you solve, if you see that can be idealized, the support system is such that it can be idealized as this, then you know how to get the flexibility coefficients. And one last case we will consider is the same beam, but now it is subjected to settlement of support. So, if the support settles like this, if the support settles like that, then what would be the corresponding so point B, there is a settlement at point B or relative settlement at point A or B, and that will cause moments at A and B. So, how these moments at A and B are related to this this delta B. So, let us consider this again. So, initially this is the beam, both ends are fixed, this is A, and this is B, right. And suppose the beam deflect like this, So, this is the settlement delta, this is the settlement delta, okay. And that delta will cause some moment at A and some moment at B. We need to find out those moments. Suppose this is MA, and corresponding moment at B is MB, okay, MA and MB. So, then what would be the bending moment, diagram? Bending moment diagram for this will be, again there is no other load in between. So, bending moment diagram will be like this. So, this is MB, we know whether MA, MB same or different, it is a trapezium, okay, MA and MB. Now, then apply the moment area method. What moment area method says that that rotation at A, the rotation at A or relative rotation, if we draw a slope at A and slope at B, their relative rotation between the angle between those slopes will be the area of the bending moment MI by the bending moment by EI diagram, this by EI diagram. Now, you see this is a fixed support. So, your slope is a horizontal line here, this is again a fixed support, slope is a horizontal line here, there is no relative rotation. So, your bending moment diagram, the area of this bending moment diagram should be equal to 0. Now, the area of the bending moment diagram if we take, then it is half into MA plus MB by EI into L, that is equal to 0. Okay. So, this gives us MA is equal to minus MB. Okay. This is 0 because if you draw a slope like this, if you draw a slope like this, and if you draw a slope like this, their relative rotation is 0. So, area of the bending moment diagram by EI diagram will be 0. That is the moment area method, the first theorem in moment area method. Let us now apply the second theorem of moment area method. Then what is this delta? This delta is essentially your rotation, your deviation of point B, the deviation of point B drawn on slope at point E, or the same delta is the deviation of point A. If you look at from this deviation of point A on the slope drawn at point B. So, what we can do is we can take that deviation will give us that deviation can be obtained by taking the a moment of this bending moment, bending M by EI diagram. Okay. So, now the delta will be, moment of this diagram if we take the area which is MA plus MB divided by 2 EI into L, that is the area of this bending moment diagram, into MB plus 2 MA divided by MA plus MB into L by 3, okay. That is delta, right. So, this you can just by some algebraic manipulation we can get, and substituting MA is equal to MB, we can get this is equal to MB into L square by 6 EI. Okay. So, what we get? We get MB is equal to 6 EI by L square into delta. So, this again we can write that this is the flexibility, this is the stiffness coefficient. Okay. So, stiffness coefficient corresponding to the settlement. Similarly, MA will be what? MA will be, MA is equal to minus MB. So, it will be minus 6 EI by L square into delta. So, this is the corresponding stiffness coefficient. Okay. So, this can be written. So, again if we see the problem is such that it can be idealized like this, the stiffness coefficient can be obtained like obtained. So, similarly for different support condition, for different conditions you can get the stiffness coefficient. Okay. Now, for that please go through the books. In books, any structural analysis book you take, there are different cases given, and please see those cases and try to derive the corresponding stiffness coefficients. And when you derive the stiffness coefficient, please be careful about the sign. Okay. All the one important thing you get, suppose if this is the stiffness matrix, all the diagonal term in the stiffness matrix should not be all these diagonal term in the stiffness matrix. All these diagonal term, in the stiffness matrix that you can see, this diagonal term should be positive. Okay. And this stiffness matrix is symmetric. And again another important term, it is positive definite. Now, what is positive definite, that we won't discuss here now, but this is a property of the stiffness matrix. I request you see any linear algebra or matrix algebra book to see what is positive definite matrix. Okay. Now, when you calculate stiffness coefficients, be careful about the sign. If you are getting wrong sign, if you get the wrong sign, then your results will be wrong. Okay. So, be careful about the sign convention. Okay. So, what we do is now, once we have understood the concept behind displacement method, and also we have understood there are two ingredients in that general formulation, that is the fixed end moments and stiffness coefficients. We have also understood how to get the stiffness fixed end moments for different loading conditions, and we also seen how we can calculate the stiffness coefficients for different boundary conditions. Next step is to derive the to write the equations for displacement methods. Now, we have three different methods that we will be discussing in this course. One is the slope deflection method, then moment distribution method, and then direct stiffness matrix. We will do this week slope deflection method, but again the underlying principle of all this method is that is just now what we have discussed in first two lecture of this week. So, next class what we do is we will start slope deflection method. Next class we will start slope deflection methods, derive the corresponding equations, and demonstrate that through some examples. Okay, then see you next class. Thank you.